So welcome everybody to the Winds and Currents webinar. Today we're fortunate to have Lionel Renault, who's going to talk about the current feedback to the atmosphere. So, and I'll let you go ahead and get started, Lionel.
Yes. Sorry. Okay, can you see my screen?
Yeah, that looks great.
Okay, full screen, that's it.
And that's the right mode. Excellent.
Okay, so hi everybody, thank you for having me here. So yes, today in my talk will deal with the current feedback to the atmosphere, and I will illustrate the impact it can have, so from a fine-scale interactions and impacts to a climate response. And I will try to focus on the limitations we have in the observations, in the current observations we have now. So this is an illustration here of the sea surface temperature. Actually, that's the mean difference between a simulation with current feedback and without current feedback, the coupled simulation over 30 years. So we can see that fine-scale interaction doesn't have only a local impact, but it can have also a large-scale impact, for example, over the sea surface temperature, especially over western boundary currents. So I will illustrate it, I will explain it after. So I wanted to really start my talk with this figure. So this is from Boucher-Eta 2020. It illustrates the biases we have in the coupled global models. So this is from the IPSN model at 1 degree model. So we can see that, as you know, I guess, that there is a large biases in sea surface temperature up to 5 degrees, say, especially over western boundary currents and eastern boundary currents. So we know that to explain those biases, some of the biases are due to the clouds, for example, but some of them are also due to the lack of fine-scale oceanic processes. And we know that by increasing the spatial resolution in our model, we do obtain a much better representation of the ocean dynamics, in particular, of course, of the mesoscale dynamics, but also of large-scale currents. However, some biases persisted or even appeared. As, for example, we have a too large mesoscale activity. We can have still biases in western boundary currents, for example, in the Gulf Stream separation or in the Gulf Stream penetration into the Atlantic Ocean. And we have persistent biases in sea surface temperature and also in in-depth temperature. And we realized that actually we are missing a sink of energy. And since a decade, or more or less, some studies focus on the role of the fine-scale Earth interactions in explaining those biases and in producing a sink of energy from the ocean to the atmosphere. So basically, in the literature, there is three main RC processes, RC interactions. First, the thermal feedback. So basically, that's the impact of the sea surface temperature on the atmosphere. So this is an illustration from Franger et al. 2013. So we know that it can have an impact on the precipitation, on the cloud cover, but also on the wind, and also a retroaction on the ocean, for example, by modulating the available potential energy. There is a wave feedback that is fully known. It may have an impact on the atmosphere, on the winds, and also on direct impact on the currents, but I won't focus on that today. And there is a current feedback to the atmosphere. So basically the impact of the surface currents on the surface stress and the overlying winds. So I will focus on this interaction today. And the main talk of this talk, basically I have two main goals, the main goals of this talk. So first, it's to illustrate the impact of the current feedback on the ocean, the atmosphere, and large-scale impact on the climate. And I will try to focus on the limitations of the current observations and the need of new observations, for example, SWOT, but also satellites like WACOM. So this is the outline of my talk. So I will first start with the direct impact of the surface current on the surface stress and the overlying wind. Then I will illustrate the partial control it has on the ocean dynamics and the indirect impact it has on the precipitations and also on extratropical storm tracks, focusing again on the limitations of the observations. So basically, what's the current feedback? So in a coupled model, basically it's very easy to take into account. It's simply the relative winds to the oceanic currents. So instead of using the absolute wind, UA, we are using the difference between UA minus UO, so 10-meter winds minus surface oceanic currents. In the first ocean model, as I will illustrate after, we do need a parameterization of the wind response. So we cannot just use simply that formula. So it has a direct impact on the surface stress and then on the wind. So this is an illustration, this is a cartoon to illustrate it. So it's, of course, it's a simple cartoon. So we have an eddy in the northern hemisphere here, for example, with a uniform wind in green. And then we can estimate the surface stress in black using the absolute wind. So we just ignore the presence of the currents. And then we can estimate the exchange of energy between the eddy and the atmosphere. Basically, that's the name we use, the wind walk, the eddy wind walk. So it's the scalar between the scalar product between the surface stress and the oceanic currents. On this side of the eddy, we have a positive input of energy because the wind and the stress is flowing toward into the same direction as the current, so that the product is positive. So there is a positive input of energy from the atmosphere to the eddy. On the other side of the eddy, that's the other way around, the current is going in the opposite side, in the opposite direction, so that the scalar product is negative, and there is a deflection of energy from the eddy to the atmosphere. So basically, when we integrate the windward over the eddy, we have a zero windward. We don't have any transfer of energy, any net transfer of energy between the eddy and the atmosphere. So eddy is not sensitive to the wind, not directly sensitive to the wind. In a forced ocean model, when we use the relative wind, so instead of using the absolute wind when estimating the surface stress, we will use the difference between the wind and the currents. The wind is still prescribed, so in green, it's still uniform, but we will have a reduction of the surface stress on this side of the eddy. And when we estimate the eddy windward, we will have a reduction of the positive input of energy. So compared to this situation. On the other side of the eddy, that's the other way around, we have a larger surface stress because UA minus UO is larger than UA, so that we have a larger deflection of energy from the eddy to the atmosphere, and the net eddy windward is negative, so that we have a deflection of energy from the eddy to the atmosphere. In a Köppen model, in the real life, actually, the wind is not prescribed, of course, it can react. So on the eastern branch of the eddy here, there is more friction, there is less friction, so that the wind can accelerate, and there is a partial re-energization of the ocean. So that if we compare here to here, we have more input of energy. On the other side of the eddy, that's the other way around, we have a larger stress that will induce weaker wind, so that there is less deflection of energy. It's a partial re-energization, but if we integrate the windward over the eddy, we still have a sink of energy from the eddy to the atmosphere. I will show you after that this sink of energy is important in determining the ocean dynamics. And actually, we can have some metrics to estimate the wind response and the stress response to the surface currents, and then we can compare those metrics to the observations. So the first metric we have is the coupling coefficient between the surface stress current, the surface current vorticity here and the surface stress curve here. And we can just do a simple scatter plot and with some binning to have a coupling coefficient, which will be the slope between surface vorticity, surface current vorticity, and surface stress curve. Here we have three experiments, like in the cartoon. In the first experiment, we don't use the current feedback to the atmosphere. We only use the absolute wind to estimate the stress. In that case, we don't have any relationship between surface current vorticity and surface stress curve. We have a slope of 0. It makes sense. In the second case, the wind is prescribed, so it cannot react to the currents. But we can see that we have a clear linear relationship, negative relationship between the surface current vorticity and the surface stress curve with a negative slope. That means that, for example, a positive current vorticity will induce a negative stress curve right on top of it. So it will have a special coherence. But in the third case, here we are in a Köppen model, so the wind can react, like in the third case in my cartoon. And in that case, we still have a negative relationship, but with a weaker slope. So here for the US West Coast, it's only minus 1.2 instead of minus 1.9. but we still have that negative relationship between surface current vorticity and surface stress current. And actually, then we can estimate those coupling coefficients everywhere over the world. So for example, here it's from a coupled simulation over 30 years at a 1/12 of a degree. Just ignore the blue, the very bluish values here. It's over the ice, so it doesn't make sense. But over the open ocean, the ocean without ice, we do have a negative S2 everywhere. S2 actually is very important to understand and to estimate correctly from the observations too, because it can be interpreted as the efficiency of the current feedback. The more negative the S2, the more efficient the current feedback. And as I will illustrate after, the larger the eddy killing we will have. And actually, we have issues with the observations. So it's an illustration here. We can have a rough estimate of this coupling coefficient using QuizCat and EBISO. So for example, here, on the top panel, I estimated S2 using EBISO and QuizCat. So we can see that's more or less negative everywhere. But actually, if we compare it to that estimated from the coupled model, we have a large difference in terms of strength. It's less negative in the observations. But we know that both QuizCat and EBISO have issues because they are very smooth. They are not coherent. And overall, we don't have the measure of the current and of the stress at the same time. So that basically it's already nice to have some kind of estimation because it shows that it's not only a numerical stuff, it's something we can observe, but we don't, actually, to me, we have no clue of the real value of S2. So maybe our model overestimated, maybe they are right, but we can only have indirect validation of the processes. And we have the same issue, we can do the same with the wind. So basically, that's the same story. We can estimate a coupling coefficient between surface current vorticity and 10-meter wind curl here. And we can estimate a slope between them. So here for the US West Coast, in that case, it's positive. It makes sense because when we have more friction, we will have less wind. So that's what I showed before in my simplified cartoon. So we have a positive slope, a positive coefficient between currents and wind. The response shows an illustration of the SW with the altitude. So the response of the wind can be felt up to the top of the atmospheric boundary layer. And we can estimate it everywhere. So here over a tropical channel. And so basically it's positive everywhere with some special variation. But actually, and here we have a larger issue, is that we don't have any observations of that, any clear observations, global and systematic observations at least. So we can estimate these coefficients using EBISO and QuizCat. But here we can see that we have a big issue because we don't have only an underestimation, but actually it's the opposite sign. SW, when we estimate it using QuizCat and EBISO, is negative instead of positive. It doesn't make sense because when we have more friction, we should have less wind. But actually, we can reproduce it using our model. So we can do some kind of synthetic data of the EBISO and QuizCat, and we can see that when we use the same approximation we have in QuizCat to estimate the winds, we can have a negative coefficients with a large difference, again in terms of strength, but this is because of the smoothness. And actually, it was already known before, the wind in QuizCat has two limitations. First, it's equivalent neutral winds, and secondly, it's relative to the oceanic currents. And we don't know the ocean, we don't really know actually the oceanic currents at the same time, nor at the same resolution, at the same spatial resolution. So basically, we cannot have an estimate of the wind response to the current feedback. And it's a pity because it has a large importance, because it will drive the wind work, the exchange of energy between the ocean and the atmosphere. We can also use those coupling coefficients. I don't have time here to demonstrate it, but actually we can use them to force an ocean model. So it can be very useful to have a light ocean model instead of a coupled ocean model. And as I will show now, it will have not only a local impact, but also a large scale impact. And we don't have any information over the equator region. So now I will show you the direct impact on the ocean. So basically those small scale, I won't focus on the large scale impact, Basically, we have a reduction of we have a slowdown of the mean current induced by the current feedback because we have a reduction of the mean input of energy from the atmosphere to the ocean. But here we focus on the mesoscalation of energy from the eddies to the atmosphere. So this is the eddy wind work. As I showed you before in my cartoon, we expect when we have the current feedback, we expect to have a negative eddy wind work. So basically a transfer of energy from the eddies to the atmosphere. We can observe it partially. Again, we have large limitations with both AVSO and QuizCat, but still here for South Africa, we can see that we have transfer of energy from the eddies to the atmosphere. In a coupled simulation without current feedback, here it's over 5 years of simulations with a spatial resolution of 6-7 kilometers. And we can see here that basically we have something noisy because we have only 5 years of simulation, but if we integrate it, basically we will have zero eddy wind work of zero. So as I showed you before in my cartoon, so the eddies will be insensitive to the wind. And here we have a coupled simulation with current feedback, and we can see that we have this large sink of energy from the eddies to the atmosphere. We can estimate them everywhere over the world ocean. So they are the larger, of course, when we have a large mesoscale activity, we will have a large sink of energy, but actually they also depend on the wind. And we can estimate them using the coupling coefficients. So again, it's important to have a correct observation of the stress and of the wind in order to not only validate actually, but also to understand the extent to which this wind work is a good estimate, or maybe it's overestimated. Because actually the wind work, this negative wind work is very important in determining the mesoscale activity. This is an illustration for the US West Coast. So that's the same simulation than before I showed you for the coupling coefficient. So this is the simulations without current feedback, coupled simulation. This is the mesoscale activity. And we can estimate it in a forced oceanic simulation using the relative wind. So the wind is prescribed. We don't have the partial winterization. And we can see that we have a drastic damping of the mesoscale activity by 55%. And when we are using a coupled simulation, so the wind can react, we have a partial re-energization, but we still have a damping of the mesoscale activity by 40%. So we can have that, the main driver, so I don't have time to show it here, but the main driver of this reduction is the negative eddy wind work. And we can also indirectly validate this simulation, this damping. Actually, we have a much better representation of eddy statistic in that simulation when we smooth like Aviso and when we compare, for example, eddy tracking, so eddy statistics with Aviso. And we have the same process everywhere actually over the world ocean. So this is the sink of energy I showed you before. It induces an eddy killing everywhere, especially over western boundary currents. So be careful, here is a logarithmic scale. So actually that blue here is very weak and it's due to a change of the path of the western boundary currents. I will show you after. And same here for the Agulhas current. So basically there is 30% reduction of the mesoscale activity. And this transfer actually, this transfer of energy, the sink of energy can be predicted, as I said before, using the coupling coefficient between the surface current and the surface stress. We can estimate it, and we can even parameterize it in a model. I just wanted to focus on that region too. So it's for the tropical instability waves. So actually, we don't have any observations there or any satellite observations, a good satellite observations. Say we do have some in situ observations, but when we compare a simulation without current feedback and with current feedback, we can see that there is a large reduction of the mesoscale activity. So it's consistent with the previous study of Small in 2009, I think. And there is a reduction of the wind work, here of the total wind work. But in that case, we don't have any observations of any good observations, nor of the wind work, because QuizCat is not very good in this region. And we don't have any satellite estimates of the surface current, of the total current. And again, for this region, so if we want to estimate the turbulent heat flux, so for example, I know that there is another satellite mission that could be launched. It's a Melody, I think. and they aim to estimate turbulent heat fluxes. But actually, if you don't consider the surface currents, then you will also have an error in the estimates of the turbulent heat flux. So this is an estimate for the latent heat fluxes. And this is the difference when we use the current or not, or we just ignore the current in the estimate of the latent heat flux. So absolute here and relative here. So basically, especially over the equatorial region, we do have an error up to 10% in the estimates of the latent heat flux. And also, I don't show it here, of the sensible heat flux. So having the information of both surface stress, temperature, and current, it's very important to have an accurate estimate, not only of the wind work and coupling coefficient, but also of turbulent heat fluxes. And I just want to know, so it's not only a local impact, but also an indirect large-scale impact, especially, for example, for Western boundary current. So this is an example for the Gulf Stream. So this is the mean Gulf Stream path in green from EVISO, the mean dynamic topography, actually. So it's we know that the path is like that, it's pretty realistic. And in black here, I have the mean Gulf Stream path, but for coupled simulation without current feedback. We can see that we have two main issues. First, there is a concave separation here. If we do an histogram here, the PDF of the separation of the Gulf Stream, we can see that in the observation, we have a very stable separation always at the same place. But in the simulation, we have a bimodal separation. So sometimes it has a kind of small overshoot. Sometimes it's too south. So basically, it's way too meandering. And post-separation, we have the same issue here. We have a Gulf Stream that is too meandering and that has too large interactions with the eddies, actually. And with the simulation with current feedback, we can see that we have a much better representation of the Gulf Stream path, both separation and post-separation. And when we look here, the PDF, we have a correct representation of the separation of the Gulf Stream. And this is because actually of the mesoscale activity that is too strong in the simulation without current feedback. There is a large, so this is what we call the cascade of energy, the flux of energy between the different scales. So this is small scales here on the right and large scale here. So this is for the aggregate current, but we have the same for the Gulf Stream. And when we activate the current feedback, there is a reduction of the mesoscale activity. There is less eddies. The eddies here are separated for the Gulf Stream from the Gulf Stream. They are interacting a lot with the Gulf Stream, making it unstable. And when we reduce the mesoscale activity, there is also a reduction of the inverse cascade of energy, so that there is a stabilization of the path of the Gulf Stream. And actually, we also have issued, again, in the observations, we can estimate the cascade, the geostrophic cascade of energy using EVISO. So I did it here, and I kind of smooth, like in the ARBIC 2013 paper, I smooth the simulations to mimic EVISO. So here we have EVISO in green, and in red, the coupled simulation with current feedback, and in blue, without current feedback. So first, it's a kind of indirect validation because we can mimic, we are closer to EVISO. But actually, to me, there is too many issues. First, if we compare the strength of the inverse cascade, it's largely underestimated by EVISO. And also the change of sign between a forward cascade and an inverse cascade is not at all at the good place. So in the model, it's 80 kilometers, but when we mimic EVISO, we shift it to more than 100 kilometers. So basically, with the observations we have now, we cannot have a good estimate of those cascades of energy that are very important in determining Western boundary currents. And I'm almost done. So large-scale impacts. So actually, those change, especially in the Western boundary currents, those change of path have also a large-scale impact on sea surface temperature and then on the large-scale thermal feedback. So here, this is the SST anomalies induced by the current feedback. So some of them are not significant, but for example, here over the Gulf Stream, so we have a change, we have a stabilization of the Gulf Stream induced indirectly by the current feedback. It changed the advection of temperature and then the SST gradients. The same, for example, for the aggregate currents. when we have less advection of warm Indian Ocean water into the Atlantic Ocean. And actually, this will alter the large-scale aesthetic gradients, and it has a large impact on the precipitation. So that's an ongoing study we are doing with Fabien Desbiol. And especially, for example, here over the Gulf Stream, we can see that we have a reduction of the precipitation due to the current feedback, and the same, for example, over the Agulhas currents, which is consistent actually. So this is done with a 30-year simulation at a 1/12 of a degree, but it's consistent with regional simulations I have, and also from CO et al. 2021. And actually, it also, so that the last one, it's an ongoing results, ongoing study we are doing. It also change in the aesthetic gradients have an impact on the extratropical storm track. So here I estimated the low deepening rate, which is an Eulerian measure of the storm track activity using that formula from Kuwano Yoshida and Midoway. Here, this is from the simulation without current feedback, so it's consistent with the literature in terms of pattern and strength. Basically, you have large positive values over western Atlantic currents, and we have a reduction. So this is the difference in terms of low deepening rate between the simulation without current feedback and with current feedback. So basically, the change in surface temperature in gradients reduce the low deepening rates, especially over the Gulf Stream and the Kuroshio. So it's still ongoing, but it's an illustration of the indirect large-scale impact of the current feedback. So I just conclude here. So it has current feedback to the atmosphere, has many impacts from regional to large scale. Actually, it has a direct impact on surface stress and winds. So we really want, I think, to have a correct estimate of both surface currents and winds and current at the same time. It induces a transfer of energy, of momentum from mesoscale, but also some mesoscale currents to the atmosphere. So in that case, it's not anymore the atmosphere that forces the ocean, but the other way around, the ocean forces the atmosphere. And actually, we can even see that at the tidal scale. And it has a large indirect effect. So for example, control of western Atlantic currents, but also precipitation and storm track. And I did not show it here, but it also have an impact on biogeochemical variability, both indirect and direct. But it has large uncertainties. As I showed before, the coupling coefficient, the wind work, the mesoscale activity, and even the mean currents in some regions. So we really need more observations to better understand the current feedback and not only validate the model, but also it's not only to validate the model, but also to better understand how our climate works. And from the observations, so we can also derive coupling coefficients that could be used to force an ocean model. So it could be very useful if we don't want to run a fully coupled model. We could just run an ocean model forced by coupling coefficient, forced using a parameterization based on the coupling coefficients. That's all. Thank you.
Thank you very much. This was great. Questions for Lionel? I see a comment in the chat, but Julien has a question. Do you want to go ahead and ask?
Yeah, I guess I just read the question I put in the chat. So thanks Lionel for this review of this field. I just wanted to know whether it's not clear to me how the coupling coefficients are supposed to vary with scales, and I just would like to know whether there's something to learn there, or whether you think that there's no issue. I'm just asking.
Well, at some mesoscale, for example, from mesoscale, it's pretty well known. Basically, we know it's not from the models, of course, but we can predict the strength of the ESTO, for example, using the large scale winds. The larger the winds, the larger the magnitude of the wind, of the synoptic wind, the more negative the ESTO at the mesoscale. At the sub-mesoscale, we don't really know actually, because first we don't have that much observations. Then there is, to my knowledge, only one study I did in 2018. And we do have that kind of relationship at some mesoscale. But actually in my models, I was a bit stuck a bit stuck by it's the same problem we have with SWOT actually, to disentangle waves from the some mesoscale signal actually. So at some mesoscale, from my estimate, it should be more or less the same, but actually we do have uncertainties at some mesoscale. Then actually, it's I was surprised, but at tidal scales, we do have the same kind of coefficient, the same strength.
So large uncertainties, but no indication that anything weird is happening.
Yeah, it should be. I mean, but then it's kind of important because if you overestimate S2, then you will overestimate the submesoscale killing, and then you will lose too large and too many energy. So
Thanks.
thank you.
If I could continue on that question, I think if we think about a potential satellite mission, one of the questions is likely to be what accuracy is needed. So how accurate do you think you'd need to measure and at what spatial scales to see the types of coupling coefficients that you're able to extract from a model?
That's a tricky question. Well, I guess to me, at least what we want to have, it's very important to have at the same time current and stress. Now, for example, with AVSO and QuizCat, we don't have only the issue with the mesoscale in AVSO, but we have the issue that they are not at the same time and they are not coherent. So basically, we are just mixing something that has a special effective resolution, say just by a random number, 80 kilometers, and another one with 100 kilometers, but we don't really know actually. So to me, we really want to have at the same, in a coherent way, both measurements. Then in terms of scales, of course, if we could have some mesoscale with a very tiny resolution, it could be great. But at first, if we could have the mesoscale, to me, that would be the main, the more important coefficient to have. Because actually, with a student of mine, we are comparing the sink of energy we can have with the forward cascade of energy. So the flux of energy from mesoscale current to some mesoscale. So the forward cascade, and we can compare it to the sink of energy induced by the current feedback. And actually that sink of energy is much larger. So we really want to have a good estimate of it. Then what is the precision? I don't really know actually. I guess from a given, in a model, we have larger, we have other errors, we have uncertainties with forcing, with other stuff. So to me, I would say 10% would be already great because it would be already, even 20% because it will be already a jump with what we have now.
Yeah, I suppose you have the capability to take your model and smooth it to potential resolution and then look at what that would do.
Yeah, that's what we did with AVSO and QuizCat. We basically smooth model like more or less like AVSO, and we did the same for QuizCat. And we estimate the cascade of energy I showed you before and the coupling coefficients. But yeah, we can. But yeah, if we have, for example, we want to do it with SWOT2 to some extent for the cascade of energy. But for example, for Wacom, it would be a very good exercise when we know exactly what kind of resolution we can expect. We could clearly generate some kind of synthetic data and mimic Wacom, sorry.
So we're actually at a stage where we get to specify what the engineering requirements are. So you could just go through a range of possibilities for resolution and dictate what the trade-offs would be. It's not clear that everything could be delivered, but it's a good time to just experiment. I see that there's a comment from Rick Danielson in the chat about questions. So
yeah, thanks, Lionel, for the talk. It's really great. My question more relates to one of your earlier plots shows the range and variability of the wind stress curl versus current vorticity. Any of those plots is good. Yeah, that's perfect.
Okay.
So in this type of plot, we're showing you're showing the variations in current wind stress curl, I think, as a function of vorticity. Is that as a function of vorticity, where vorticity would be taken to be the reference, I think. Is that right? So in other words, the vertical, the variations are shown as
Yeah, basically, yeah, I did not precise the methodology here. Yeah, basically, we did like Dudley Chetton did for the thermal feedback. We smooth, we kind of smooth, we filter the data using a temporal filter, more or less 1 month, to estimate the anomalies of the of both stress curl and current vorticity.
Okay, fair enough. Okay. So the question in doing that, in making the two measures, scaling the two measures, or making the two nevertheless, the even if the scales are similar in the two measurements, you could by symmetry, right? You could also plot the variations in the opposite measure. So basically, putting the error bars horizontal. There are horizontal error bars, I guess, is what I'm trying to say.
Exactly. Yeah.
Right. So and then with reference to error bars that could be vertical or horizontal, there's some range in the slope, and that's the key question: is how much coupling, how strong is the coupling? But the general problem is, sorry?
You mean the error we are doing in the slope estimate?
No, I'm not saying there's an error. I'm just saying that, well, I'm just saying that you have some flexibility within the error bars of where you put the slope.
Yeah. Actually, it's here in the title of the, for example, in the coupled simulation, it's minus 1.2 plus minus 0.35.
Yeah. No, yeah, fair enough. Right. I see that, yeah, I acknowledge that there's a range. So the prediction of the, basically, what we're trying to do is kind of refine the estimates, right? I think that's I think not just your initiative seeks to refine the coupling estimate, as well as as other groups trying to refine the coupling estimates. It'd be nice to see some convergence, but the question I suppose I would ask is, since we are looking at a linear coupling, what we're actually trying to get to is the nonlinearity in the relationship between these two measures, right?
Yeah.
In a sense, I mean, there is this strong linear coupling, but physically we're trying to ask where is the coupling nonlinear, because that's where we'll have the biggest challenge, I think.
Well, yeah, I agree. That's where in some regions with large non-linearity,
Right.
yeah, we have larger uncertainties using that kind of coupling coefficient. Yeah,
Right.
I agree.
Right. The nonlinearity in the atmosphere might be somehow related to the temporal variations, where shorter timescale variations may be where the spatial nonlinearities in the ocean might be more important. Who knows? But the anyway, so it's just the plots are interesting to me, maybe not so much to everybody, but there's a certain degree of uncertainty I would place on both measures in this case. I'll leave it there. So that's probably enough.
Thank you.
Thanks. Bia, I think, is next.
Hi, Lionel. Thank you so much. That was great. Kind of going back to Sarah's comment and Julian's comment, I wonder if you have a feel for what are like the scales for the time response of these feedbacks, because you were arguing that you need to, yeah.
Yeah, the time response actually it's less than an hour. It's actually, well, if you trust the models, it's a kind of a direct response. And actually, you can see it, for example, for the tides. I did a simulation so with tides and coupling, and you can see that you can generate a tidal wind and a direct surface stress response and a direct wind response actually. So it's a very fast response.
Thank you.
Thanks. Brian.
Hi, Lionel, great talk. And I apologize if you said this and I missed it, but as you imagine, I'm quite interested in your cascade calculations,
Yeah.
where you showed the effect of, if you smooth it, it looks more like a vehicle.
Well, it's based on your paper.
Yeah. So the one thing I was kind of wondering is, and maybe you said this, if I missed it, I'm sorry. Is this a cascade calculated from the geostrophic approximation applied to SSH, or is it directly from the velocities?
That's a good question, because here in what I show you here, it's from the geostrophic currents. But actually, if that's something we are also missing, if we wanted to have a clear estimate of the forward cascade, we need to have the total currents. We are missing a part of the cascade because, in the observations, I mean, because we have only access to the geostrophic currents. But in the model, in those plots here, because I wanted to be able to compare to EVISO, I used the geostrophic currents.
Great. Yeah. So I just wanted to just mention to Sarah and everyone else that, I think at this early stage, you're looking for, things to sell the mission with, right? And I think this cascade thing could be a big thing because, Scott and Wong calculated it from altimetry and some of the rest of us have done it from models, but we've tended to focus on, calculating it from the geostrophic part. But if you actually have the velocities, you can get the cascades due to, internal waves and all these other ageostrophic things that we love. So I don't know if you're looking for a list of bullets to sell the mission. I wonder if that could be part of it. Does that make sense what I'm saying?
Yeah.
It does, because we did estimate those cascades using the total currents. And yeah, you can clearly see, well, at the large scale, I mean, it's more geostrophic, so you won't have that much difference. But if you look really at small scales, but not only 2 kilometers, I mean, less than 100 kilometers, you will change your cascade of energy and especially your forward cascade of energy. So here basically, we don't have at all a good estimate of the forward cascade of energy. It doesn't make really sense to.
Yeah, because a lot of that is, internal waves are probably involved and they're not balanced. So
no.
And I guess also related to that, I wonder if an OSSI would be worth doing where you put, you estimate the cascade due to the total velocities, and then you put potential error bars from the mission in there to see, just how clean that would be. Sarah, you probably thought of all this already, but.
I think that would be great. And yeah, I don't think anybody's agreed to do that yet. So volunteers, welcome. I will say in general, in selling the mission, we have many audiences we have to sell it to. So at one level, we're trying to figure out how to sell a potential mission to taxpayers, to our grandparents and the person sitting next to you on the airplane and the guy you run into in the supermarket. And all of them have to believe this is the best possible way we can spend their tax dollars. And at the other end of the spectrum, we need to sell this to ourselves, to people who have a really detailed understanding of the technical value and who will say, well, is the uncertainty actually exactly enough to compute this obscure quantity that we really care about? So we're talking to a lot of audiences and we need to gather the evidence for all of them. Which is why we need everybody on this call involved in thinking about this and participating.
Yeah, it's a fair point. Maybe cascades of energy are not for the person next to you on the plane, but
But they're still good
For our community, I think it's a big deal.
yeah, and a lot of this matter, you know, if what sells it to the general public is something about getting better weather forecasts and a better understanding of the whole climate system and the Earth system, then the cascades are part of that. And we just have to find the simple story that we can share in public while we go off and geek out about cascades. So it's a lot of different strains to keep track of, and it's going to take all of us to keep ourselves in line, thinking about how to get all of them right. Fabrice has a comment in the chat. Do you want to go ahead and ask that, Fabrice?
Yeah, just to so a question, but the question is related to the how we actually want to use the data and what the effects we want to put in, going from whatever is measured, sigma naught and Doppler to stress and velocities and how we deal with stability effects and other things. So just to clarify how you actually did your computation of the work with the QuizCat data, and then how we think we may want to do that with Wacom in the future.
Well, in my estimate here, basically I use what to me QuizCat and Wacom will be the same. Basically, it's to me it's my interpretation at least. It's a measurement of the surface stress, and then we can derive the wind. And that's the reason why the wind actually is not the equivalent neutral wind speed that is relative to the surface currents. So basically here I use the surface stress, but then in that plot here I use the wind from QuizCat. So that has both issues, first equivalent neutral winds, and then relative to the surface currents. We don't know. But if we knew the currents, we could derive the neutral wind speed response to the ocean currents. Is that clear?
I think that's kind of clear. Yeah, I mean, I understand what you do with the observations. And then in the model, because in the model you also have, I don't know what kind of stress you have, and you actually have some effect of air stability on the stress and what you do with that, and how do they compare?
Yes, in the model I use it's in WRF in the atmospheric model we use Ferral-Etal bug formula. But then in the model we can, that's what is nice with the model, we can mimic a QuizCat. So basically here I estimated from my surface stress, I estimated the equivalent wind in the model relative to the ocean currents. So basically with the models you can mimic the limitation of the observations. You can do it both. Here I did not smooth, but you could imagine that you smooth the data, like QuizCat, for example, temporally and spatially, but you can also reproduce the fact that the wind is first estimated from the surface stress. Not exactly the surface stress, but kind of.
Okay, and then you can also validate directly the modeled stress with the observation, I guess.
Yeah, more or less. But
Range.
then, for example, in the case of
Statistically,
QuizCat, the large scale, for example, in the equatorial region, the large scale winds, the large scale stress in QuizCat is largely biased. So basically, we still have issues with that. But in other regions, yes.
Okay.
But you cannot really validate the response to the surface current because in the observations, that's what I wanted to illustrate it here. So this is the coupling coefficient S2 estimated from the observations, ABSO and QuizCat, and from the models. And you can see that we don't have the same strength. So, but to me, maybe we have biases in the models, but we know that we do have large uncertainties in the observations, both ABSO, that is very smooth, and QuizCat. And they don't have the same smoothness. So to me, that's if they add the same smoothness, it could be more valid, but they don't even have the same defaults. So it's makes harder to have a good estimate of the
Yeah.
stress response.
Marcus, I see you have a hand up.
Yes, sorry, I couldn't find the hand. Thank you, Lionel. I've, of course, followed you in a few presentations, as you know, also at ICM. And thank you for this very interesting presentation. Maybe a comment before I go to my question is that we know and we find there's many other errors in the model, in the atmospheric model, which of course, when you do this type of, let's say, a simple approach of looking at sort of deficiencies of the spectrometer and put them in the model simulation world, you cannot reproduce, yeah, because we know that models cannot really resolve moist convection, at least the dynamics induced by moist convection, gap winds, causal effects. So there's so many things that go on. Also SST coupling, which I guess Dudley can talk about this. So there's many other things, many other limitations from the model. And then when you try to simulate, let's say, the so-called limitations from the spectrometer, these are sort of embedded in your simulation. So this is we have actually published a bit on this, so maybe we can interact offline. But my question was more related to the sort of mission requirements, because from what I hear, let's say the jackpot would be to have consistent and almost instantaneous, simultaneous winds and currents, and then those at the same scales and so on. From one side, what I see, you talk from Bia's comment that actually the response is sort of instantaneous. So you would really like to have these two things collocated in space and time. But then you can put it on the, let's say, coupling perspective, and you can find your parameterizations and then work it out on the model. The other is that if you really want to depict this at the local scale, let's say, both in space and time, because those couplings can change regionally and seasonally, etc., then you would like to have more and more coverage, I guess, so a better, richer coverage. So if we look at the sampling requirements, what would you like to have? Because Wacom is just a single instrument, as far as I know, yeah, which will have some limitations in terms of temporal sampling. SWAP would have even more limitations, of course, in terms of temporal sampling. So what would be your, let's say, wish list in that sense?
Yes, well, to respond to your comments, yeah, I agree that we do have large uncertainties in the models. And for example, in the estimates of STO, it does have a sensitivity to the atmospheric boundary layer you use. So of course, I don't have the exact number. Of course, it's not it's not a 100% sensitivity, but as a rough number, I would say we have between 5–10% uncertainties only with the atmospheric boundary layer. But we should do more tests actually to have to test more options. And in my wish list, but we already know that Wacom, we have a daily coverage, right? Would have.
That's the hope, yeah.
Yeah.
That's the requirement right now.
Yeah, so to me, a daily coverage, so it's my wish list, of course. So it would be already great. If we could have more, it's even better, but then that's just impossible. So for now, at least. And well, in terms of accuracy, right, I guess we may have the same issue that with QuizCat, with the precipitations in the equatorial regions. So I don't really know how we can deal with that. And in terms of scales, the mesoscales, I mean, if we could have good estimate of scales more than, I don't know, 50 kilometers, something like that, or even less, I mean, the better we have, the more happy we are. So I don't really have I don't really know.
Yeah, maybe just to add another comment on the model errors. the big issue here is that those errors are systematic. Yeah. So yeah, in a simulated world, you can probably better deal with random errors. But systematic are probably a bit more difficult to tackle, I guess.
Right. I think, can't we
And
hope
thank
that
you
a
very much.
satellite mission will help with the systematic errors?
I hope to see you in Barcelona soon, by the way.
Hopefully.
Well, any last questions before we finish up? I think we could spend a long time talking about near inertial oscillations and their potential impact on this, but
Yeah.
but that might be something for another day. This was a great talk. Thank you very much.
Thank you very much for having me.
Really appreciate this discussion. So a big round of applause for Lionel, and we'll hope to see everybody. We're still rounding up a speaker for next week, but I hope we'll have somebody. So stay tuned.
Bye. Thanks.
Thanks a lot.